The goal of this first lesson is to understand what we call a digital system. As a first step, we will try to define the more general concept of physical system. It's not easy, it's even impossible to give a general definition of what a physical system is. Nevertheless, we can underline some of their important characteristics. We could say that physical systems are sets of interconnected objects or elements that realize some function and are characterized by a set of input signals, a set of output signals, and obviously some type of relation between input and output signals. Furthermore, every signal is characterized by its type, could be a voltage, a force, a temperature, and so on, and is characterized by a range of values. In the case of a voltage, all the voltages between some minimum and some maximum value. Let us see a first example. It is a system that controls the working of a boiler used to heat a room. There are two input signals. The signal pause is the position of a selector that allows to define the desired temperature. The other input signal is temp. It's the value of the temperature as measured by a sensor. There is an output signal on-off with only two possible values. On, get started the boiler, and off, stop the boiler. In this example, the relation between inputs and outputs is defined by the following piece of program. It is a continuously executed loop, and it's easy to understand the control algorithm. First rule: if the temperature measured by the sensor is smaller than the temperature defined by the position of the selector minus some margin, let us say half a degree, then the boiler must get started and the on-off signal, output signal, must be equal to on. A second rule: if the temperature is greater than the temperature defined by the position of the selector plus the same margin, then the boiler must get stopped and the output signal must be equal to off. If the temperature were between the position minus the margin and the position plus the margin, then the boiler state doesn't change. The boiler state, I mean running or not running. After that, wait for 10 seconds, and that's all. So that, with this control algorithm, the room temperature will be equal to the reference temperature with a precision of about 1 degree and with a response time not much longer than 10 seconds. Which are the type and the range of the input and output signals? The signal position represents the selector position between two extreme values, for example, between 10 and 30 Celsius degrees, so that its range of values is this one, any value between 10 and 30. Signal temp represents the ambient temperature measured by the sensor, assuming that the sensor is able to measure any temperature between 0 and 50 degrees, its value belongs to this range of values. Finally, the on-off signal, output signal, has only two possible values, on and off. Signals such as position and temperature that can take any value within a continuous and thus infinite set of values are called analog signals. Signals such as on-off, whose values belong to a finite set of values, in this case a two-element set, are called digital or also discrete signals. Let us see a second example. The second example is the time computation component of a chronometer. It has 4 input signals. 3 of them are generated by push buttons. Those signals are reset, start, and stop. The fourth one is generated by an oscillator. It's a clock reference, ref, and it is a square wave, that is an electrical signal with 2 values, for example 0 volt and 1 volt, and with a period equal to 1/10 of a second. There are 4 output signals that control the chronometer display. Those signals are H, that correspond to the display of the house, M, corresponding to the minutes, S, corresponding to the seconds, and T, corresponding to the 10th of seconds. In this example, the relation between inputs and outputs is defined in natural language. First rule: when reset is pushed down, then the output signals H, M, S, and T must be equal to 0. Second rule: when start is pushed down, the chronometer starts counting, adding 1/10 of a second at every positive edge on the reference signal. Positive edge, I mean, if this is the reference signal, those are the positive edges. And the third rule: when stop is pushed down, the chronometer stops counting, so that the signal H, M, S, and T represent the latest elapsed time, expressed in tenths of seconds. What about the range, the type, and the range of this second example? In this case, all input and output signals are digital signals. Actually, reset, start, and stop are generated by a push-down button so that their values are on or off. The clock reference signal has only 2 values, 0 and 1 volt. H has 24 values, from 0 to 23. M and S have 60 values, from 0 to 59, and T has 10 values, from 0 to 9. Systems of this type, I mean systems whose all input and output signals are digital signals, are called digital systems. We propose you an exercise. Try to describe the working of the chronometer in a more formal way, that is, with a piece of program using instructions similar to those used to describe the boiler control. For example, instructions such as if some condition, then do some operation, else do another operation, or while some condition holds true, loop, and then a sequence of operations, or simply a continuously executed loop. Furthermore, you could use a variable ref positive edge equal to true when there is a positive edge, I mean a 0 to 1 transition on the signal ref, the clock reference, and equal to false in the contrary case. And you could also assume that a procedure update with parameters H, M, S, and T that adds 1/10 of a second to the elapsed time, to the current elapsed time, has been previously defined. Here is an example of solution. it's a continuously executed loop. Then, first rule, if signal reset is on, then H, M, S, and T must be equal to 0. If reset is not on but start is on, then here we have another kind of loop that says that while, as long as stop is off, then if there is a positive edge on the reference signal, then update the chronometer state and nothing else. Summary of this first lesson. We have seen the definition of digital signal and of digital system. For that, systems are considered as black boxes with their inputs and output signals and with some type of relation between inputs and outputs that define their behavior. Two examples of input-output specification have been shown using pieces of program, also called pseudo-instructions.